We now return to thinking about neural nets and training neural networks, and the second part of a really important part of the computation for you to train neural networks, which is the gradient descent algorithm. We've already talked about backpropagation, which gave you an infrastructure to be able to compute how to walk downhill in a very high dimensional state space, because what we're doing is picking very simple activation functions, looking at essentially a chain rule that allows us to do things. But then there's still the question of how do you compute at such large scales, which are required for many of today's modern neural networks. And one of the really important innovations around this was not just, gradient descent has been around for a long time, but what's called stochastic gradient descent. The combination of backprop and stochastic gradient descent are really what allowed this thing to take off, right? We have bigger and bigger computers now, but even as we go to scale, there's so much computational power required to do these things that anything that can make it more efficient or for us to be able to compute these gradient directions better, make a huge impact in terms of actual training of neural networks. So stochastic gradient descent is the second part to go with backpropagation, which are the key enablers, in some sense, the foundations of how this is being driven forward. Now, since their implementations and times that we've been doing it, there have been many advances. So I don't want this to come across as if this is state of the art. This is more showing you the foundational building blocks that have allowed the emergence of neural networks to go to scale and how to train deep neural networks. And of course, if you look at the literature now, people are always working hard at better training algorithms, better ways to do some kind of versions of stochastic gradient descent, or some better architectures for neural networks for fitting the data. Okay, but that's not going to be talked about right now. What we're just talking about is sort of the foundations of why this works and how it works at scale. So again, we're thinking about the machine learning, specifically using the neural networks. And neural networks, the big issue with them is they have a lot of parameters to train, and the backprop, stochastic gradient descent are what really enable this. Remember, this is all curve fitting, however. Just want to emphasize that again. All of this is curve fitting, very fancy curve fitting. All right, so let's talk about gradient descent. Gradient descent is typically something people are somewhat familiar with. It's just it's a way to take some high-dimensional data or landscape and find a way to walk downhill. We compute a gradient and we walk downhill. So the term gradient, right, shows up in so many different application regimes. So most people have a familiarity with what gradient descent means, right, which is to walk downhill in an optimization scheme. But what we want to focus on was called stochastic gradient descent, because this is the big transition allowing us to train large-scale neural networks, is to sort of do this new procedure, which is called stochastic gradient descent. And stochastic gradient descent, in a nutshell, basically says, instead of looking at all my data and finding the best way downhill, I randomly sample small subsets of the data to have them tell me which way downhill, then sample another random subset, have them tell me which way downhill is, and so forth until I converge. In fact, after I've sampled all of my data, as I've done this, that's called one epoch, typically in training. Okay? So the idea is to randomly subsample your data. So first of all, by looking at the subsamples, it's much more rapid to evaluate which way downhill is versus I have to go through all of my data. Okay, that's one huge thing, is it's so much faster. The second really big advantage here is, in a very high dimensional landscape, it's littered with all kinds of local minima. But by sampling different data set points, it really helps you not get stuck in a specific local minima. So the stochastic gradient descent serves two purposes: speed and getting out of a lot of local minima. Okay, so let's talk about what it is. Okay, let's get to the next slide. All right, so first of all, remember, we describe some objective function. Let's call it E, the error, which is I have an input to some targets, and I'm trying to basically put in data and actually get my targets correctly. Okay, and so that is, and what I'm going to try to do is minimize the error in doing that. That's what E is. Now A1, A2, and through A of M I'm going to call these matrices I'm going to store all the weight values in a matrix between layer 1 to layer 2 to layer 3. So A1 are all the weights that go from layer 1 to 2, 2 is from 1 to 2, 3 is from 2 to 3, and so forth, all the way through. So in a deep neural network architecture, is like a feed-forward architecture, these are essentially, the A's represent the collection of weights at each layer, okay? And so what I'm trying to do is minimize this error with respect to all of these weights, A of J's. Okay, so that's the objective. And of course, this can be huge, right? So in today's modern neural networks, you can have billions of parameters in there, right? For fitting a neural network. So it's very large scale. So it's very different than the traditional curve fitting, which is like, I fit a line or parabola, which has like 2 parameters or 3 parameters. Now we're talking a billion parameters. And so I've got to take the derivative with respect to all these parameters to find which way to go downhill. Okay, that's how this thing works. All right, so essentially we optimize then, so all of this is an optimization procedure. And so now let's get very specific. So I'm going to do here, this is the root mean square error. Here's my model F that takes the input X with all these weights and tries to match the target output Y. So I take a data point X of K, it's supposed to be Y sub K, but this will approximate, let's say, some Y tilde of K. So whatever I put X of K in, it's going to give me some approximation to the Y, and this is giving me the distance to the actual Y squared. So this is a root mean square error from what my approximation is to the target. Okay? It's a very standard thing, and we're just going to stick for now with root mean square error, because that's the simplest thing to work with. All right, so the way gradient descent works, we've already talked about it, is I want to walk downhill. How do I walk downhill? I take some function space and I find its gradient. And so here the gradient will give me the uphill direction. And so I go in the opposite direction with a learning rate delta. In other words, a step size delta. So my solution, my updated weights, and X now are all my weights. Okay, so all those A matrices are now in one giant vector X. And so X of J plus 1, here's my old weights. And typically the way most machine learning algorithms start these things is they will make this a random vector. So here's a random set of weights. So you start with a random set of weights. You find which way is downhill. You take a delta step in that direction. You have a new set of weights. And now you evaluate again which way is downhill. And then you take a step forward. And you keep doing this and iterating until you reach some convergence criteria that you might specify. Okay? Now, in practice, this learning rate plays a big role in the success of your training. It also plays a big role in how fast your algorithm is. If you take a big learning rate, it's taking big steps in gradient descent towards that solution. And of course, that's great. It speeds up your code. But sometimes you can take such big steps that it walks right over where your minima is, and you can't get to it because you don't take small enough steps. However, you take really small steps, then it can take forever to converge. In practice, people often will change the learning rate as they train. So when they first start this thing, you might believe that you're far away from the solution, so you take larger deltas, and then as you get closer, you take smaller and smaller deltas until you step onto some nice local minima that you learn. Okay? So that learning rate is a terribly important hyperparameter in practice that you would use to train your neural networks. All right, so what are we going to do with this? Well, so first of all, the way we're going to think about this is in terms of error, and let's look at how the gradient descent is working currently, right? So the idea is to take all my weights, find the error to get a gradient direction, step in that direction. But now what we're going to do, so the way the error works here, right, the error is going to be a sum over all the data points. So in other words, E of K is for the kth point, what's the error at the kth point between its approximation to where the target is and what the actual data point Y of K is? What about the Y of K plus 1 point, Y of K plus 2? So this is essentially, E is the total error, but the total error is made up of all the component errors. In other words, for every data point that I have in my system, what's the error for every data point? Sum it up. That's the total error, okay? And so here, let's just look at the error for the kth point. E of K here, it's right here. So I have all these weights, and so remember, it's whatever function I'm fitting here. F of k is now looking at the function evaluated at the kth point. So whatever my neural network is doing, I shove in at that kth point. I ask the question, how well does it actually match the target, y sub k? So remember, the data points are like my training data. So maybe I have 10,000 training points. Then I would have to walk over all 10,000 points to ask, what's the error for each of these 10,000 points, okay? And then this is a root mean square error. You see I'm squaring it right over there. So this is what traditionally gradient descent will do, is do this entire sum, okay, to compute the downhill direction. So if I have, let's say, 1,000,000 data points, I've got to compute 1,000,000 here to figure out how to go downhill, okay? That's a very expensive task. So what stochastic gradient descent does instead, potentially, is you say, well, what if I just query some points, or in this case, a single point, and say, this point here, which way does it think downhill is? So instead of looking at all 1,000,000 points, I just pick one point and say, okay, my update rule is going to be my weight is going to be updated by the following. The weights in the future is what it is now. Gradient descent based upon what this kth point tells me downhill is. So you could compute this stochastic gradient descent based upon a single point. Now, first of all, if you have 1,000,000 points and now you only have one point you're querying, then this is going to be 1,000,000 times faster to do. So your code just sped up significantly, right? Because now you're doing a lot less work in that computation. But of course, using a single point may not be the best idea. What if you pick a bad point, really sets you in the wrong direction? So instead, what people do is they pick k points or p points. And so this is represented by k here. K is you pick p randomly selected points. Okay, so out of those 1,000,000, you might say, I want to pick 50. And the 50 is what's called a batch size. Okay, so batch sizes and learning rates are two of the big hyperparameter tuning issues that you have to worry about. But the batch size is just basically to figure out how to go downhill in this with these 1,000,000 points. I'll pick 50 randomly, have them tell me which way downhill is, take a step in that direction. And then what I can do in the next step, I pick another 50 randomly, which way is downhill. And then another 50 randomly, which way is downhill. Once I've walked through all the data, that's considered an epoch, okay? An epoch. I don't know how to say that. So anyway, E-P-O-C-H. So we take these we go through these epochs as we train, and you're walking through all the data. So all the data eventually does contribute to telling you which way downhill is. It's just that they contribute in batches. So batch size comes right here. Learning rate comes right there. These are two of the key hyperparameter tunings that you have to do when you train neural networks. In fact, you already start to see this. Neural networks are going to require a lot of work on your part. Specifically, you start to see, for such large scale with all these parameterizations, you're going to have to do a lot of work in hyperparameter tuning. And in fact, that is often one of the most underappreciated or understated things that's going to happen to you if you decide to do neural networks is you're going to spend a lot of time hyperparameter tuning. Very rarely can you just take a model, run it, and it works. You have to find the right hyperparameters to get it to work. And this is just often a painful process. There are many methods now being developed to automate this hyperparameter tuning exercise because it is costly in terms of time, in terms of training models, but you're already starting to see it. And it's not like these parameters maybe offer marginal improvements. If you don't pick them right, the neural network doesn't even work at all. And often you're looking for a little island of where this thing works in this hyperparameter tuning space. So learning rate, batch size, all these things really matter when it comes to training neural networks. So that's kind of the key ideas. So gradient descent, right, is sort of this workhorse algorithm that we have been using in the mathematical sciences for a long time in optimization. And what it's always done is just try to like walk downhill, find a minimum of something. But now, when we come to the context of machine learning, right, we're walking downhill in some very high dimensional space with lots of local minima. And so there's first the issue of just can you compute at that level? And so stochastic gradient descent is a really viable pathway forward to being able to do computations at scale, right? Because you're randomly subselecting small batches, figuring out how to go downhill, updating the weights. Second, it's very easy to compute the gradient direction because you're using the back propagation on activation functions that you have analytic expressions for what their values are. So between these all, it's very easy to sort of, well, not easy. You have the infrastructure that allows you to go train large-scale neural networks. And already you're starting to see the things that are going to be involved in this. You're going to have to hyperparameter tune. You're going to decide size of your neural network, the depth of your neural network, the learning rate, the batch size. These are like, there's 4 parameters right there that you've got to figure out how to pick those in order to get the best results possible. And there's more parameters that you have to tune, including, you get to pick activation functions that might work or might not work. So a lot of choices you're having to make in this architecture, which is just simply a curve fit at scale.